We're gonna find the optimal solution, one row at a time. StatQuest. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to talk about the Simplex Algorithm and we're going to go through the mathematical details. This StatQuest is brought to you by the letters A, B, and C. A always, B, C curious. Always be curious. This StatQuest is also brought to you by Gurobi. Gurobi, which has always been free for academics, provides a state-of-the-art optimization solver used by leading companies around the world. Gurobi powers decisions in logistics, energy, finance, and beyond. If your goal is not just to understand optimization, but to put it to work, Gurobi is the solver trusted by experts. To learn more, check out the links in the description below. In the StatQuest, Optimization with Linear Programming, Main Ideas, we learn the main ideas of linear programming. Specifically, we saw the main ideas of how the Simplex algorithm finds the amounts of cookie and donut mixes that maximize revenue, given these constraints. The Simplex algorithm starts at the origin, and then moves to neighboring vertices that increase revenue, until moving to the next vertex does not increase the revenue. Bam. Now that we know the main ideas of how the Simplex algorithm works, let's look at the nitty-gritty details. This will either be fun and cool or incredibly painful, so you might want to brace yourself. Note, one of the painful things about the Simplex algorithm is that there's a lot of inconsistency in how its terminology is used. So, to spare you some of the agony, I'm only going to mention terminology that is used relatively consistently. Small bam. Anyway, this region that contains the feasible solutions is called the feasible region. So the idea is to find a vertex on the edge of the feasible region that gives us the optimal values. Next, the equation we want to optimize, in this case the equation for revenue, is called the objective function. Then we have the constraints. Note, for the Simplex algorithm to work, the variables, in this case cookie and donut mix, must be greater than or equal to 0. And this makes sense because we can't have negative amounts of either mix. Anyway, combining the constraints and the assumption that the variables are not negative gives us the feasible region. Now, for the Simplex algorithm to work properly, the shape of the feasible region must be such that for any 2 points along the outside, like these, we can draw an uninterrupted straight line between them. In other words, these need to be linear equations. And, among other things, that means we can't use the cookie or donut mix variables as exponents. Another way to think about it is that shapes like this won't work for the Simplex algorithm, because a straight line between these 2 points is interrupted by the shape itself. Also note, in this example, all of the constraints use the less than or equal to symbol. In contrast, if you have a constraint with the greater than or equal to symbol, like this one that requires us to make at least 5 kilograms of mix, then you need to multiply everything on both sides of the inequality by -1, so we can flip the condition around to be less than or equal to. And if you have a constraint with the equals symbol, like this one that requires us to make exactly 15 kilograms of mix, then we replace the equality with 2 inequalities, one with less than or equal to, and one with greater than or equal to. Now the 2 inequalities give us a sort of inequality sandwich that is the equivalent of the original equality. However, because we can't have the greater than or equal to symbol, we multiply everything in that equation by -1 and flip the symbol to be less than or equal to. The purpose of ensuring that only the less than or equal to sign is used in the constraints is to simplify the algorithm and make it so that we don't have to check for different possibilities at each step. Next, we convert all of the inequalities into equalities By adding extra variables, called slack variables, to every equation, including the objective function. The idea is that when the total amount of something, like flour, used by the cookie and donut mixes on the left, is less than the amount available on the right, the slack variables make up the difference. For example, imagine we made 10 kilograms of cookie mix and 8 kilograms of donut mix. Now the combined cookie and donut mixes would only use 8 kilograms of flour. And this would be less than the 10 kilograms of flour that we are allowed to use. So we make up for the difference by setting slack f, which is the slack variable for flour, to 2 kilograms. Note, since this equation is focused on flour, the slack variables for sugar, slack s, and chocolate, slack c, are both multiplied by 0, and thus go away when we do the math. Anyway, when we do the math, the total on the left matches the amount on the right. Likewise, the slack variable for sugar, slack s, compensates for when the total amount of sugar in the mixes is less than 5 kilograms. And the other two slack variables are multiplied by 0, so they go away. Lastly, the slack variable for chocolate, slack c, compensates for when the total amount of chocolate in the mixes is less than 1 kilogram. Note, adding slack variables to the objective function is just a formality since all of those coefficients are 0. Now all 4 equations have the same format. They are all equalities, and they all have the same variables. The only differences are the coefficients, the numbers we multiply each variable by, and the totals. Now we put all of the coefficients and totals into a matrix. Note, the value for revenue starts out as 0 because when we search for the optimal vertex, we start at the origin. Now we multiply every value in the first row by -1. This is just a convenience that allows us to use the simplex algorithm as it is usually defined. Now, technically, we're done formatting the matrix for the simplex algorithm. However, just to make it easier to keep track of things, I like to add a dotted line that separates the coefficients associated with the objective function from the other values, and another dotted line to separate the left sides of the equations from the right sides. Lastly, I like to label each column so I can remember what it represents. Now we're finally ready to see how the simplex algorithm maximizes the revenue. Anyways, starting at the origin, the first thing the simplex algorithm has to do is decide if it should go up along the cookie mix axis or over along the donut mix axis. One way to make this decision is to look at the first row of the matrix and identify the largest negative number. In this example, the largest negative number in the first row, -3, is in the first column, the column for cookie mix. So we could decide to go along the cookie mix axis. Alternatively, we can calculate which neighboring vertex will result in the largest increase in revenue and go there. However, for all of the examples in this StatQuest, we'll just use the largest negative number in the first row method. Now, by eye, we can see that, of these 3 points along the cookie mix axis, only this point is within the feasible region. However, the simplex algorithm can't see, so it figures out which of these 3 points is within the feasible region by testing all 3. And the way the simplex algorithm tests all 3 points on the cookie mix axis is by dividing the totals for the constraints by the corresponding positive numbers in the cookie column. The results of this division are the cookie mix coordinates for each point. The highest value, 25, corresponds to where the yellow line intersects the cookie mix axis, and that point is way outside the feasible region. The middle value, 16.7, corresponds to where the blue line intersects the cookie mix axis, and that point is also outside of the feasible region. Lastly, the lowest value, 10, corresponds to where the brown line intersects the cookie mix axis, And finally, that point is on the edge of the feasible region. So, in general, the simplex algorithm selects the lowest value because larger values must be outside of the feasible region. Note, if there were ties in the smallest ratio, it is common to just select the row with the lowest index. Now, because we used the first column and the last row to decide to move to this vertex, the simplex algorithm will use the first column and last row to modify the entire matrix so that we can continue to explore other vertices around the feasible region for a vertex with a larger revenue. Now, if you are already familiar with Gaussian elimination or row reduction, then what happens next will make perfect sense. In contrast, if you're not already familiar with Gaussian elimination or row reduction, then what we're about to do will probably look completely bonkers. That said, just know that the next steps are part of a systematic process that can identify where lines intersect. In other words, we're going to use a process that can identify coordinates of vertices around the feasible region. The first thing we do is multiply everything in the last row by 10 in order to get a 1 in the bottom left-hand corner. Now the goal is to add multiples of the last row to all of the other rows so that, excluding the 1 in the fourth row, every other value in the first column is 0. For example, because the third row has 0.3 in the first column, we multiply everything in the last row by negative 0.3, and then add those products to the third row, to end up with a 0 in the first column and third row. Likewise, because the second row has 0.4 in the first column, we can multiply everything in the last row by negative 0.4, and then add those products to the second row, to end up with a 0 in the first column and second row. Lastly, if we multiply everything in the last row by 3, and then add those products to the first row, we end up with a 0 in the first column and first row. Now, in the first column, the column for cookie mix, we have a 1 in the fourth row, and everything else is 0. The 1 in the fourth row of the cookie mix column is then paired with the 10 in the totals column. Combined, the simplex algorithm interprets that to mean that the coordinate along the cookie mix axis is 10. In contrast, because the second column, the donut mix column, is a mishmash of values other than a single 1 and a bunch of zeros, the simplex algorithm interprets that mishmash of values to mean that the coordinate along the donut mix axis is 0. Thus, with the coordinate for cookie mix set to 10, and the coordinate for donut mix set to 0, the coordinates for our first move are 0, 10. Also, as a bonus, the value in the upper right-hand corner, 30, tells us the revenue at 0, 10 is 30. In other words, if we plugged the coordinates for the first move, cookie mix equals 10 and donut mix equals 0, into the equation for revenue, we'd get 30. Bam! Now that we have moved to 0, 10 and calculated the revenue at this point, 30, the simplex algorithm has to decide where to go next. By eye, we can see that the only neighboring vertex is this one, which would require us to increase the amount of donut mix we make. However, like we said earlier, the simplex algorithm doesn't have eyes, so it can't see what the next move should be. So, instead, we determine the next direction to move by looking for the largest negative number in the top row of the matrix. In this case, the largest negative number, negative 2, is in the second column for donut mix. So the simplex algorithm decides to move along the donut mix axis. Now the simplex algorithm has to figure out how far it should go out along the donut mix axis and still be within the feasible region. By eye, we can see that there are two possible intersections. And the simplex algorithm tests them both by dividing the totals for the constraints by the corresponding positive numbers in the donut column. The results of this division are the donut mix coordinates for each point. Note, we didn't divide 10 by 0 because 0 is not a positive number. Anyway, the highest value, 12, corresponds to the donut mix value for where the yellow line intersects the brown line. And that point is outside of the feasible region. The lowest value, 10, corresponds to the donut mix value for where the blue line intersects the brown line. And that point is on the edge of the feasible region. Again, in general, the simplex algorithm selects the lowest value because larger values are always outside of the feasible region. Now, because we use the second column and third row to decide to move to this vertex, we multiply everything in the third row by 5 in order to get a 1 in the third row, second column. Now the goal is to add multiples of the third row to all of the other rows so that, excluding the 1 in the third row, every other value in the second column is 0. Now, because the last row already has a 0 in the second column, we don't have to do anything to it. In contrast, because the second row has 0.5 in the second column, we multiply everything in the third row by negative 0.5, and then add those products to the second row, to end up with a 0 in the second column and second row. Then we multiply everything in the third row by 2, and then add those products to the first row, to end up with a 0 in the second column and first row. Now, in the donut mix column, we have a 1 in the third row and everything else is 0. And that means the first two columns, the cookie mix column and the donut mix column, each have a single 1 and everything else is 0. Like we saw earlier, the 1 in the last row of the cookie mix column is paired with the 10 in the totals column. And this tells us that the cookie mix coordinate for this point is 10. And now the 1 in the third row of the donut mix column is paired with the 10 in the totals column. And this tells us that the donut mix coordinate for this point is also 10. Thus, with the current value for cookie mix set to 10 and the current value for donut mix set to 10, the coordinates for a second move are 10, 10. And, like before, the value in the upper right-hand corner, which is now 50, tells us the revenue. In other words, if we plug the coordinates for the second move, cookie mix equals 10 and donut mix equals 10, into the equation for revenue, we'd get 50. Double bam! Now we can see that by moving from 0, 10 to 10, 10, we increase the revenue from 30 to 50. So, the question now is whether or not there is some combination of cookie and donut mixes that can increase revenue even more. In other words, if we move to this vertex, could we increase revenue even more? And to answer this question, the simplex algorithm does the same thing it did twice before. The simplex algorithm determines the next direction to move by looking for the largest negative number in the top row of the matrix. However, at this point, there are no negative numbers in the first row of the matrix, so we are done. In other words, the point 10, 10, which represents a revenue of 50, is the best we can do given the constraints on the amount of flour, sugar, and chocolate that we can use. Triple bam! Now that we understand the simplex algorithm, let's use it to optimize a slightly fancier situation. Specifically, we're going to walk through exactly how the simplex algorithm can optimize the fancier problem that we originally saw in the StatQuest optimization with linear programming main ideas. However, before we dive into this slightly fancier example, I need to give credit where credit is due. The next example is loosely based on one in Robert Sedgwick's 1983 book, Algorithms. and I discovered it on Daniel D. Souther's webpage for a course taught at the University of Hawaii at Manoa, and the link is in the description below. Anyway, in the earlier StatQuest, we saw how the Simplex algorithm finds the amounts of donut, cookie, and brownie mixes that maximize the revenue, given these 5 constraints. And, as we saw before, since we now have 3 variables we need to optimize, donut, cookie, and brownie, we will draw everything on a graph with 3 axes. The first constraint creates this plane, and each remaining constraint creates a different plane. Now, if we assume we can't make negative amounts of donut, cookie, and brownie mixes, we end up with this 3-dimensional surface. And the goal is to find the vertex that represents the optimal values for donut, cookie, and brownie. Now let's dive into the nitty-gritty details of how the Simplex algorithm solves this problem. However, first, because the equations are going to get really big with tons of slack variables, we replace donut with x, cookie with y, and brownie with z. Bam. Now, just like in the last example, we convert the less than or equal to symbols to equal symbols by adding slack variables to all of the equations. However, this time, since we have 5 constraints, we need 5 slack variables, 1 per constraint. For example, for the 5th constraint, we add 1 times S5 to the equation, plus 0 times all of the other slack variables. For the 4th constraint, we add 1 times S4 to the equation, plus 0 times all of the other slack variables. The 3rd constraint has 1 times S3, the 2nd constraint has 1 times S2, and the 1st constraint has 1 times S1. Lastly, we add 0 times all of the slack variables to the objective function. Now we put all of the coefficients and totals into a matrix. Then we multiply the top row by -1. Now we use the top row to decide which direction we should move first from the origin. And since we have a 3-way tie for the largest negative number in the first row, -1, we pick the one furthest to the left. Since the column furthest to the left is for the x-axis, we start by moving out along the x-axis. Now we determine the coordinates for the first move by first dividing the totals by the positive values in the first column and selecting the row with the lowest value. And then we use Gaussian elimination, or row reduction, to set all values in the first column to 0 except for the 5th row, which is set to 1. Now, focusing on the columns for x, y, and z, since the only column with a 1 in it and everything else is zeros is for x, and the corresponding total value is 8, we know that the coordinates for the first move are 8, 0, 0. Now, because the column for y has the largest negative value in the first row, we'll focus on the second column. Now we determine the coordinates for the next move by first dividing the totals by the positive values in the first column and selecting the row with the lowest value. Then we use Gaussian elimination, or row reduction, to set all values in the second column to 0 except for the selected row, which we set to 1. Now the corresponding total values for the 1s in the x and y columns are 12 and 3. So the coordinates for the next move are 12, 3, 0. Now, because the column for z has the largest negative value in the first row, we focus on the third column. And we determine the coordinates for the second move by selecting the 6th row to work with. Then we use Gaussian elimination. Now the corresponding total values for the 1s in the x, y, and z columns are 12, 3, and 4. So the coordinates for the next move are 12, 3, 4. Now, because the column for S4, the fourth slack variable, has the largest negative value in the first row, we focus on the seventh column. And we determine the coordinates for the second move by selecting the third row to work with. Then we use Gaussian elimination. Now the corresponding total values for the ones in the x, y, and z columns are 9, 9, and 4. So the coordinates for the next move are 9, 9, 4. Lastly, since there are no negative numbers in the first row, we are done. And the revenue for 9, 9, 4 is 22. In other words, the optimal values are the coordinates 9, 9, 4, and they result in the revenue equal to 22. Triple bam! Now it's time for some shameless self-promotion. If you want to review statistics, machine learning, and AI offline, check out the StatQuest PDF study guides and my best-selling books on machine learning, neural networks and AI, and statistics at statquest.org. There's something for everyone. Hooray! We've made it to the end of another exciting StatQuest. If you like this StatQuest and want to see more, please subscribe. And if you want to support StatQuest, consider contributing to my Patreon campaign, becoming a channel member, buying one or two of my original songs or a t-shirt or a hoodie, or just donate. The links are in the description below. All right, until next time, Quest on!